A2 Further Maths Reduction Formula. Okay, so what I'd like you to do is see if you can work out the integral of x squared cos 3x. Okay, so just pause it, give yourself enough time to do it. Okay, so let's see what you did then. Hopefully you noticed that the best way to do this is looking at using integration by parts. Because you're doing integration by parts, it's the x squared that you want to differentiate and the cos 3x that you want to integrate. So once you've used integration by parts, you ended up with this answer just here. The problem is when you come to doing the integral at the end, so this part of the integral, you'll notice that to do this, you're going to have to use integration by parts again. Okay, so if you didn't get that far before, pause there, see if you can finish it off. Okay, so you've had to use integration by parts a second time. So if you used integration by parts a second time, hopefully you would have come down to a solution like this. Just be careful with your negatives. There's going to be lots of negatives floating around. We can see that that's where the positive comes from, just there. When we integrated the sign, which was negative makes a positive. We've also got a negative here from when we got the negative for a second time. So you just be very careful with your negative signs. Once you've done that, now we've reduced it down to something that can be integrated straight away. So now we can integrate this part and hence comes out this answer. Don't forget the constant of integration just there. Okay, so well done if you managed to do that. Right, what I'd like you to do is I'd like you to have a go at integrating just once that integral just there. So just do it just once and see what you get. Okay, so pause if you need to. Let's have a quick look then. So hopefully you did something very similar to the previous one. You used x to the power 5, you tried to reduce it down, and you reduced it down to that, but you'll notice that this part just here, you'd have to use integration by parts again to try simplifying that. Okay, but instead of doing that, what I'd like you to do is just have a go at this one. Something similar. Have a go at integration, using integration by parts just once. See if you can get that. See if you can spot a pattern coming out. Okay, so hopefully you did exactly the same technique. There was no difference there at all. You looked at differentiating that one, integrating that one, and what you ended up with is something like that. And now hopefully you've started to spot a little bit of a pattern. These two are quite similar, except there are different powers of x, and you'll notice there's some sort of pattern going on with both of these. What I'd like you to do though is I'd like you to have got a general form for it then. If I had a look at this sort of form, so these two fall under that one, because either one's an n to the power n equals 10 or n equals 5. So what would it be if I asked you to integrate that function just once? What would you get? Okay, so hopefully when you did it, you got that answer. You notice lots of similarities here. This function always had a half at the front, same power there, very, very similar for each one. This one here, this was 10, the same as that was the power 10, that was 5, the same as that was power 5. That's why that's an n just there. But what's important is that this function here, this integral just here, is almost exactly the same as the original integral, except the n value has reduced down to 1. So what we can do is we can rewrite this using what we call a reduction formula. Okay, right, just grab your notebooks. So a reduction formula is something you use to hopefully make the integration a little bit easier. All right, so what you're going to do is you're going to find a formula that shows you how to do the integral, and instead of having to do integration by parts every single time, you can use a reduction formula to help you work it out. Okay, right, so let's use that example we just did. So that example we just had, we saw that the integral of x to the power n e to the 2x can be written like this. Right, we just saw that. So how do I write this as a reduction formula? Well, what I can do is I can call that initial integral, the one we were trying to work out, in. I stands for the integral. So the integral to the power n. And what I notice is my end answer is always the same here. So this bit's going to be a half x to the n e to the 2x. That bit's going to be exactly the same. But this part just here is still going to be minus n over 2, but then you're working out the integral of x n minus 1 e to the 2x. Now, because this is exactly the same as this one, except the n has been replaced to n minus 1, what I can do is I can write it like that. And I've noticed that my answer, as you can see, is a reduction formula. All right, because it's reducing that integral, which was to the n, down to n minus 1. So it's reduced it down once. Then what I could do is I could use that one, and I could rewrite the integral form, the reduction formula again, and replace it for there, and that would get me n minus 2, and so on until I get down to n equaling 1 or n equaling 0, depending on which one I want. Okay, so sticking with your notebooks, let's have a look at writing down this exam question and see how we solve it. Now, by all means, start it off. You might want to do the integral bit yourself, or you might want to just pause and we'll work through it together. Okay, so you can choose. Okay, so pause if you still need more time copying it down. Okay, so we're looking at integrating x squared ln x to the power n. So I want to integrate that. And then I want to do it because I want to get a reduction formula that will make this integral a little bit easier to work out. Okay, right, so let's try that then. So the first thing I need to do is use integration by parts to see if I can figure out what the reduction formula for this is. So if I did that, the x squared is getting integrated, the ln x to the power n is going to be differentiated. Okay, so I want to be looking at that. Notice that I had to do it that way around. Normally you pick the x squared to get differentiated, but you really want to differentiate the ln x because ln x differentiates to 1 over x. Okay, so it sort of overrides the fact that you differentiate the x squared, which seems quite interesting because you're hoping to reduce it down. You might have thought that straight away. Oh, the x squared, it's only 2 steps. X squared goes to x and then goes to a constant, so it's quite easy. But it's the ln x that's messing you up in this case. Okay, so I've made the decision. U is going to be the ln x. That's going to get differentiated. This bit is the bit that's going to get integrated. So how do I differentiate ln x to the power n? I would differentiate using the chain rule. So ln x goes to 1 over x. Okay, so that's where the 1 over x comes from. If you imagine that's a 1 at the top. And then I differentiate the function to the power n. Now the function to the power n, the n comes to the front and you decrease the power by 1, which is where this comes from. The n comes to the front, you've decreased the power by 1. So you differentiated the function and got du over dx. Then I can look at x squared and I can integrate that, which of course goes to x to the power 3 over 3. Or a third x cubed. Okay, so I've just done integration by parts, the same as you would do normally. Now what I can do is I can use the formula and I get down to this. So this bit's okay. This bit I think I can neaten up a little bit. So I've done this part times this part. I noticed the x cubed can cancel with that x and get an x squared. I could potentially pull out a third. So I'm definitely going to get something like I could pull out the n as well, couldn't I? Because the n is a constant. So n over 3 could come out and I'm left with x squared ln x to the n minus 1, which is absolutely perfect because my original function is very, very similar to that. So let's just neaten it up. There we go, n over 3 x squared ln x to the power n minus 1. Now I'm in a position to write the reduction formula because there's my original integral. So that's my I to the power n, because it's an n power there. And then this one will be an I to the n minus 1. So I can replace the I to the n for that function. And what I end up getting is the reduction formula that I wanted. So from now on, instead of having to do integration by parts every single time, I can make use of this reduction formula. Okay, let's show you how to do that then in the second part. So pause if you need some more time to get anything down. If not, let's have a look at the next bits. Okay, so now that I've got the formula, I can then consider which number, which n value I'm looking at in this case. Now in this case, I've noticed that the n value, just here, just there, is 2. Okay, it's got nothing to do with the x squared. It's got to do with the fact that that n is getting replaced by 2. So the integral with n equals 2 is going to go to 1/3 x to the 3 ln x to the power 2 minus 2 over 3 I to the 2 minus 1, which is 1. So that's where this part of the formula comes from, me just substituting 2 into our reduction formula. So once I've substituted 2 into the reduction formula, I'm done. Then I can move on to this I to the 1. Now I to the 1, I can use the reduction formula again. I don't need to do any integration, I don't need to do any work. I can literally just copy this out, exactly the same, but this time n equaling 1. So that's what I've done here. Notice I've used the reduction formula for a second time. Okay, so each time you're just replacing the I part using this integration for this reduction formula. Notice now though, I've got down to I0. Now if I replace n equals 0 in here, in the original, rather than looking at the reduction formula, I've noticed I'm going to get x squared ln x to the power 0. And I know that anything to the power 0 is 1. So this is the point where the reduction formula would get down to something you could just integrate straight away, which will be x squared. So at this point just here, we can stop. We could see it from here if we wanted to, but you notice that just here, when you substitute in 0, you're going to get to the I to the minus 1, which makes no sense at all. So that's where this bit collapses. Okay, or n equals 0, so there's nothing there. So it works the same way if you substitute it in, but it's always a good idea just to notice that when you get down to 0, just check, is that where it finishes? Yes, it is in this case. So therefore I can just substitute that one in. Notice I've substituted it into this formula. So therefore I'm done. I can just simplify this out. So I'm going to get a third x cubed ln x squared minus those two can go together to make 2 over 9, and then these ones can go together to get 2 over 27, and so on, plus c. Okay, so a lot easier than having to do integration by parts over and over again once you've got that reduction formula. Okay, pause if you need more time. Okay, so I'd like you to have a go yourselves. It says in the notebook, so it'd be a good idea just to do it on a rough piece of paper. And while you're considering it, just write it down in your notebook, please. So I want the reduction formula for that. So pause there, get it down in your notebook, have a quick go yourselves. Okay, what I would say is if you tried it once, if you tried to do integration by parts once and you weren't happy with the answer, just try doing it a second time and see what happens. Okay, so pause there, have another go. Okay, so let's see what happened then. So when you did it once, the problem was, because the fact that cos changed the sign meant that you couldn't just replace this for in, because this bit, although it's close, it's sine instead of cos, this isn't in minus 1. So I don't blame you for stopping there and saying I'm stuck now because this bit doesn't work. Okay, so my hint to you was try it a second time. Now, because, as I just said, because of those two being different, we have to try it a second time. Now, if I tried it a second time, basically, I'm just looking at this section just here. And this is similar to the very first question I asked you when we started looking at reduction formula. Can you work it out? You notice you had to do it twice. So in this case, it goes to sine cubed. And then when I use integration by parts a second time, you're looking at this bit just here. Then you get this part minus this bit just here. So I've done integration by parts twice. Now at this stage, I can look at it and say, well, there's my original integral, x to the n cos to the x. And now I've got the other integral on the other side, which is really, really similar. Both coses, both cos 3x. But this bit is 2 less than that one. So hopefully you can guess what's going to happen. If I call this in, all right, so this bit's going to be in. This bit's all the same, but this bit is the same, but this bit here is going to be in minus 2. And there's absolutely nothing wrong with having a reduction formula that doesn't go from in to in minus 1, but in fact jumps down 2 places. So I could replace something like, for example, I to the power I6, so that would be x to the power 6, and what's going to happen is this one here will be I4 because it'll be 6 minus 2, and then you can put I4 into here and you'll get the next one down, which will be I2, and then you can put the 2 in and then it stops because it goes down to 0. So you can actually do it like that, no problem at all. Okay? And yes, it also works for even numbers and odd numbers, which we'll show now. Okay, so in your notebook, just have a go using the reduction formula. So you have to use your reduction formula to see if we can work out what sine to the power 5 x is. Okay, so I know you've got multiple different ways of working this out, but in this exam question, they're looking for you to use a reduction formula. Now, the truth is they will give you a few more hints. They wouldn't just expect you just to do it on your own. Okay, so what I'm going to ask you to do is write it down in your notebook and then we'll work through it together. Okay, so the problem is you can't just work out sine to the power 5. You might think I'm going to try doing substitution. And if you try doing substitution, what happens is you end up with this extra cos function that you haven't got anything to do with. So what we need to do is we need to write it a different way. And this is the hint you will probably get told in that exam. So what I could say now is, look, stop there, write this down in your notebook, and then have a go at this yourself now to see if you can spot some sort of pattern. Okay, with that hint. Okay, so let's see how far you got then. So now I've got sine x, sine n minus 1x. Okay, I've taken that out so it's still exactly the same. It is equivalent. I can now use integration by parts. Leave alone, differentiate, whichever bit I like. So I'm going to choose to differentiate the sine to the power n minus 1 because that's going to be a bit easier to differentiate. This bit is the bit I'm going to integrate. Okay, so what I get is when I differentiate this bit, the n minus 1 can come to the sine x can be differentiated to cos x, and anything to the functions of power n minus 1, the n minus 1 can come to the front, and then you've got the function to the n minus 2. If I integrated this bit, I'm going to get v equals minus cos x. So I've differentiated that one, I've integrated that one, and now I can substitute it into the formula. So we end up with sine nx equals minus cos x sine n minus 1x plus n minus 1 of the integral of cos squared sine n minus 2x. Okay, now don't blame me for looking and going, well, this looks very different to this. All right, it hasn't really worked out, has it? Because I've got an extra cos squared. So at this stage, what I'd like to do is sort out the cos squared. Okay, so if I asked you what cos squared is, you could quite comfortably say cos squared is the same as 1 minus sine squared. How does that help me? So if I replace it for 1 minus sine squared, I can neaten this part up here. I am going to get a sine n minus 2 times 1. I'm going to be stuck with that. But this times this is going to get me just a sine n part to it. Okay, so I've separated it out, but I've also separated out the integrals. All right, just to demonstrate what's going on here. So this times this is going to be the same as that. Okay, because it's that times 1 times that. So that's where that comes from. And that's good because that looks like it's a reduction formula just there. Started with n, went down to n minus 2. But the other part was this, the n minus 1 times sine squared times sine cn minus 2. When you add those powers together, you get sine n. Now this bit isn't part of it doesn't seem to be part of the reduction formula because it seems the same as the original. But that's quite a good thing because that's the same as the original. What I can do is I can take that to the other side. And if I take it to the other side, what's going to happen is you're going to end up with 1 plus n minus 1 lot of that. So just convince yourself that this is true. If you take sine x to the power n and you add n minus 1 lots of it, you'll notice that the sine nx and that sine nx will cancel out, but you're left with the n sine x, which is what you've got just there. Okay, and so that's where that's come from. This part is the same, so that hasn't changed. This part is written right there, that hasn't changed either. All that's happened is this got took to the other side and cancel down to that. Right, at this stage then I can stop, because that to me means I've got my reduction formula. I can see I've got my IN just there, and I've got my IN minus 2 just here. So I can rewrite that. In terms of a reduction formula. Notice what I've done just to have IN on its own. I've divided by N there and there. If you've replaced it for IN first and then divided by N, that's perfectly acceptable. There's nothing wrong with doing that at all. Okay, so I've got this. Right, now I've got my reduction formula, I can look back and see what the actual question's asking us. So the question's asking us, can we use this reduction formula to work out sine to the power 5? So I'm looking for I5. Okay, so if I'm looking at I to the power 5, I can replace that in for 5. I can replace this for 5 minus 2, which is 3. Don't forget I'm putting the numbers in as well, so that's where the 5 comes from there. 5 minus 1 is 4, that's 5. Now the I to the 3, I can use my reduction formula again. Here's my reduction formula. That I to the 3 is going to go to 1 over 3. 3 minus 1 is 2 over 3. 3 minus 2 is 1. So I end up with that. Now at this stage now, notice that I've got I1. If I try putting it back into here, what's going to happen is this bit is going to go to 0. This bit here would go down to 0 as well, sine x times 0. So I'm left with just 1 over 1, which of course is just 1, cos x. So if I put this value back in, I'm just left with minus cos x. Okay. The other option you might have is to say, look, when I equals 1, can't do it, so let's just make sure I go back to this with the power 1, which is exactly the same as that. So if I did it like that, going back to the original saying, look, it's just the same with 5 sine x to the power 1, then what happens is you can get the minus cos x that way. Okay, right, so what have I done? I've worked it all out. So you can see where the 4/15 comes from. You can see where the 8/15 comes from there. Obviously, the integral of sine goes to minus cos, okay, which is the same answer, like I said, if you put it in there. And now I can just work this value out by substituting in the top limit minus the bottom limit. And I should have, if I've done it correctly, 53 over 480. Okay, so what I'd like you to do, please, is have a go at exercise 9E on page 218.